Hey everyone, lesson 6 in our functions unit. The inverse of a relation. Now this is actually, the inverse is covered in both lesson 6 and lesson 7. So we're going to look at a few things about the inverse in lesson 6 and then we're going to continue on to lesson 7. Okay, so first of all, we've talked about, it's funny because the name of the unit is functions, and set of functions, the word function, we've probably said, 500 times already, but we haven't talked in detail on what a function is, okay? So let's talk about that for a minute. So we have relations, which are really a relationship between two sets of, well, in this case, numbers. And a function is a particular relation in which each element of set A is mapped onto one and only one element in set B. Okay, so let's take a look at this first one. So A is mapped onto an element in B, which is 2. Okay, 2 is mapped to 4, 3 is mapped to 6. So this, you notice this little phrase up here, that kind of describes what the relationship is. 1 is half of 2, 2 is half of 4, 3 is half of 6, etc. Okay, or we could have something like this. We have these numbers in A, these in B, so -2, here's the relation, is the square root of 4. Also, 2 is the square root of 4. Okay, now both of these are functions because for one element in the first A, or the domain, for one element in the domain, there is only one corresponding element in the range. Okay, even here, -2 only has one element in the range. 2, only one element in the range. Okay, now let's talk about the inverse. So an inverse is basically a relation that which undoes what the function does. So up here where it was is half of, if we turn that around and say is double, okay, that would undo the half of. We would map it back. And so 2 is double 1, 4 is double 2. Notice all of the elements in B, or the elements in B switch to the first, the domain, and A switch to the range. Okay. This one, same idea. 4 is the square of 2. 4 is the square of -2. Okay. Now, let's talk about what's a function. So in the first case, this one here, the inverse is or is not a function. So for one element in the domain, there is one and only one element in the range. Well, that seems to be true, so is a function. And for this part, double I, the inverse, which is here, this is your inverse. Okay, for one element in the domain, there is one and only one. No, there isn't. Okay, for 4, there is a -2 in the range, and for 4 in the domain, there is also a +2. So therefore, the second one is not a function, the inverse. Okay, now you'll notice because to find the inverse, we switched the elements around, the domain and range. So the domain of the inverse is the same as the range of the original. And vice versa, the range of the inverse is the same as the domain of the original. The inverse may or may not be a function. Okay, there's no guarantee there. As you can see in the second one, it turned out to be not a function, even though the original was a function. Okay, we are going to skip to the next page. Okay, we're going to look at basically 3 ways to find the inverse of a function. And this first way is to find the inverse of a function that is defined by ordered pairs. Okay, so here is our function over here. We have essentially 1, 2, okay, and then 2, 4. So we need to kind of fill that in, okay, and 3, 6, and 4, 8. Oops. Brackets around that. Okay, so there's our function described as a set of ordered pairs. Okay, the inverse of the function, remember how the inverse works, right? We switch the domain and range around, so switch these two elements around, which means that these ordered pairs would switch. So 1, 2 now becomes 2, 1. Okay, so let's fill in the rest of those ordered pairs. That should be 4, 2 instead of 2, 4, 6, 3, and finally 8, 4. Notice that the ordered pairs for the inverse can be obtained by interchanging the first and second coordinates of the ordered pairs of the original function. This reinforces the rule that the domain of the inverse is the same as the range of the original, and vice versa. Range of the inverse is the same as the domain of the original. Okay, let's try example number 3. Consider the function defined by the following set of ordered pairs. Okay, here's our ordered pairs. Describe the inverse of the function by a set of ordered pairs. So they basically want us to take these ordered pairs, switch x and y. You guys go ahead and do that. I'll do that as well, and then we'll check and see if we have the same answer. Pause your video. Okay, so check these ordered pairs, make sure that you have the same as well, but essentially what we did was we switched x and y in each of these ordered pairs, and that gives us the inverse. All right, next step, graph the original function and the inverse. So we're going to plot points for the original function, okay? I'm going to use dots, okay? And for the inverse, I am going to use x's to plot those points. I'll probably use different colors as well. So you guys do that as well, and we'll check and see if we have the same graph, okay? Okay, so I have the original graphed in red here. Oh, and I said I was going to use x's. And the inverse graphed in blue. Okay, which looks great. Part C, draw a line which acts as a mirror between the original function and its inverse. So if you kind of look at these points, it seems that there may have been some sort of line. And it looks like it might have been like here, right? That these points might have been reflected over. Okay, does that look about right? Yes, it does. Okay, so that looks like our mirror line of which the original would have been reflected over onto the inverse. Now, part D, state the equation of the mirror line. Well, you notice, first of all, it's a straight line. So if we think y equals mx plus b, the b is our y-intercept. It crosses at 0. Okay, so we'd have y equals and then plus 0. And our slope, up 1 over 1, up 1 over 1, appears to be 1. So our equation, just to simplify that a little bit, would be y equals x. That is the equation of the line that we reflect over when we have an inverse. Okay, let's look at the next page. Okay, here's another way we can represent a function, and that's to define it using a graph. So we're also going to find the inverse of a function defined by a graph. So to do this, to determine the inverse of a function defined by a graph, we're going to reflect the graph of the function in the line y equals x, because we discovered on the last example that's the line of which it's reflected over. So it says alternatively, though, you can select the coordinates of some key points, interchange the coordinates, switch x and y in other words, and plot new points, which really is what we did with ordered pairs, right? Except we didn't have the graph. We took the ordered pairs, switched x and y. So I actually prefer that method because sometimes it gets a little tricky on exactly where it would be if you're reflecting over that line. So we're going to do that. Sketch the graph, the inverse. Okay, is the inverse a function? Okay, so there are some key points that they've given us on this graph, and we're just going to write them down here. So here's our original, and then inverse. Okay, and we're going to come up with the inverse coordinates. Okay, so original, let's start with this leftmost point. Now, be careful on here. Notice each square on the grid, okay? It goes from 0 to -10 here. And there's only 1, 2, 3, 4, 5 squares. So each square must be 2 then. So that means this point would be at -6, okay, 2, 4, 6, and 0. There's our original point. So on the inverse, that point would become 0, -6. You switch x and y. Okay, just going to emphasize that up here. Switch x and y. All right, let's do another point. This would be 0, and notice the vertical scale as well. Every square is 2, so we would be at 0, -6. do the inverse, switch your x and y, we'd be at negative 6 comma 0. Okay, this point over here on the far right would be 6 comma 0, inverse 0 comma 6. Okay, so if we plot our inverse now, 0 comma negative 6, so that'll land right here. Negative 6 comma 0, that lands here as well. Okay, and 0 comma 6 would put us right here. Okay, now we move from left to right. This was our middle point, so we know to draw it like that, and then this one like that, and there's our inverse. Okay, now it asks, is the inverse a function? So we talked about how for one element in the domain, there's one and only one element in the range. So let's say we kind of take a place here at negative 2. Okay, so at x equals negative 2, we have a value of 4, and we also have a value of negative 4. Guess what? Not just one element in the range corresponds to that element in the domain. So this is not a function. Now, when you're given a graph and you're testing to see if it's a function, the easiest way to do that, same idea, that was supposed to be a vertical line, let's try that again, is the vertical line test. Okay, if a vertical line passes through a function more than once, it's not, or sorry, if it passes through a relation, not a function, more than once, it's not a function. Okay, so the vertical line test, okay, passes through graph greater than one time, not a function. Okay, so this obviously is not a function. All right, let's take a look at the next one. Okay, once again, we're going to get the points, we're going to switch them to get the inverse, and then we're going to graph it and analyze whether it's a function or not. You guys go ahead and do that, and then we'll check back, see if we have the same thing. Pause your video. Okay, so did we get the same looking graph, I hope? All right, so just a couple things that I wanted to mention that I forgot to mention last time on the last example. Again, this is an inverse, so it should be reflected over the line y equals x. So if you take a look at the line y equals x, kind of going like that, this one did look like it was reflected over that line. Let's draw this one here. So if we draw a line through y equals x, okay, so we'd have to go through negative 10, and positive 10 to do that. Okay, you'll notice that it is reflected over that line. And also notice where these two graphs cross is actually on the line. Same thing here, although that has more intersection points as well. Okay, now finally, vertical line test to see if it's a function. And vertical line would pass through it more than once, so therefore not a function. Okay. Let's go to the next way that we would find an inverse, and that's if we are given the equation of the function. Okay, now we have been doing this all along, we just haven't been doing it algebraically. This is essentially what you would do. Two easy steps. Interchange x and y, or switch x and y in the equation, and then you solve for y. Okay, so we're going to look at example 5. Consider the function defined by the equation y equals 3x plus 2. Okay, find an equation in the form y equals mx plus b for the inverse of the function. Okay, so really we're going to start with y equals 3x plus 2. Okay, interchange x and y, or switch x and y. And what that means is y becomes x becomes y. So y becomes x, and x becomes y. So now our equation is x equals 3y plus 2. And they want us to find the equation in the form y equals. So we need to isolate this y term here. All right, so to do that, first thing we do is get rid of the 2 from both sides. So subtract 2 from both sides. And then we would have to divide both sides by 3. So x minus 2 divided by 3 equals y. And there we go. Now they do want in mx plus b, so we're going to divide that 3 into each one. 1/3 x, okay, like 1x divided by 3, minus 2/3. And now we have it in the proper form. Okay, we're going to do the rest of this example in part 2, so we will see you guys in part 2.